All right, so welcome to this PODS session where all the Sigma people are having coffee. So this session is enumeration algorithms. Actually, the first three papers are all on problems related to triangle listing. The first talk will be given by Professor Michael Goodrich on using cuckoo hashing for solving the triangle listing problem.
Thank you. So this is joint work with David Epstein, Michael Mitzenmacher, and Manuel Torres. Manuel is an undergraduate student who will be going to graduate school next year at University of Illinois. So the problem that we address in this paper is the triangle listing problem, where you're given an undirected graph you can think of as a social network, and you'd like to enumerate all the triangles, all the cycles of length 3 in this graph. For whatever reason, perhaps you're somebody who studies social networks and is interested in these triads of friendship that somehow is indicating these small communities of very close friends, and you want to find out all these communities of friends. A related problem that we study in this paper as well is the set intersection problem. In fact, we're going to be using this as our inner loop subroutine for solving the triangle listing problem. In this case, the problem is to pre-process a collection of sets so as to quickly answer set intersection queries. Or in the database community, this of course would be known as an inner join that we'd like to do between two sets represented as tables. And here the idea is you are allowed to spend some time pre-processing these sets to put them into a nice data structure of some kind, so that then hopefully when you do this query for the set intersections, that goes much faster than what would be known without just simple pre-processing. So then how can you use this to solve the triangle listing problem? There's a very simple algorithm that is probably even the first thing that anyone would kind of think of if they start thinking about this with respect to how you would design an algorithm for the triangle listing problem. Namely, assume that your graph is represented in some kind of an adjacency list format, where you have the adjacencies for every vertex stored in some kind of a set representation. And then for every edge, simply go to the adjacency list for the two endpoints of that edge, V and W, and intersect those two sets. Every element that's a member of both of those sets must necessarily now be forming a triangle with the base edge E. So a very simple algorithm, not all that efficient in the way that I've just described it. Runs basically in M times N time, so not so great. And where M is the number of edges and N would be the number of vertices. And it also suffers from the unfortunate side effect that triangles will be listed more than once. And so then you have to do some sort of a post-processing to purge out duplicates with this algorithm. So pretty much nobody uses this algorithm in its vanilla form. Instead, there's a whole family of algorithms that are more or less equivalent in some sense to this approach, where you order the vertices of the graph in some way, either by their degrees or, in this case, I think a little bit more sophisticated but still incredibly simple way to order the vertices is by something called the k-degeneracy order. And the k-degeneracy order is an ordering such that you number the vertices 1 through n, and then direct all the edges, always going from a lower numbered vertex to a higher numbered vertex. And so they're always having these directions as an orientation. And you create this numbering by a very simple greedy algorithm, where you first just take the vertex that has the smallest degree, that vertex is number 1, then take the vertex that has smallest degree among the vertices that are left, that's number 2. And then at each stage of the way, always just keep selecting the vertex that has smallest degree with respect to the remaining vertices. And you do this just by that very simple-minded greedy algorithm, and you get what is commonly referred to as this k degeneracy order. Every vertex will have out degree k. And it turns out in practice, many social networks, for example, social networks that follow power law distributions, will have bounded degeneracy. People have done experimental studies of social networks to show that typically k is around 20, maybe 15 for most social networks. If you're familiar with planar graphs that can be drawn in the plane without crossings, if you just follow that greedy algorithm on a planar graph, you find out that it has a degeneracy order where k is 5. In addition, there's a related concept that in this literature has also been very popular, and that's this concept of arboricity, or in this notation I was using A of G for this notation. That refers to the number of spanning forests that will span all the edges of the graph. And that's a little bit more esoteric, but as it turns out, this k that you get from the k degeneracy order is always within a factor of 2 of the arboricity. And so people will then characterize the running time of algorithms based on, say, k degeneracy in terms of this arboricity. So, in fact, if you go back to the original paper by Chiba and Nishiseki, that's how they characterize it in terms of this arboricity, and I think that then sort of created a precedent for following papers. And then this paper by Ortman and Brandeis is a beautiful paper that showed that the slew of dozens and dozens of other algorithms on triangle listing basically run in the same running time if you're careful. And you just order the vertices in the right way, you basically get the same running time of m times the arboricity. And the improved algorithm is very simple and now runs in this running time where you now just for every edge only intersect the outgoing adjacency lists. Every triangle now will just be listed once because you've sort of uniquely oriented how every triangle will be listed. And you automatically get that the running time is m times the arboricity because the size of each of those outgoing adjacency lists is bounded by the arboricity. So that's sort of the previous work and reviewing of how work has gone before, coming up to modern times. So the revisit that many of us have now taken in more modern times is to examine algorithms not in the traditional RAM algorithm that theoreticians like me grew up with, but to look at more realistic computational models that take into account the fact that computers store words in their memory, not just abstract numbers. And in particular, we assume that every memory cell in the computer is represented with the word of some W bits, and you're allowed, with respect to those words, to do the common bit parallel operations that you see in many CPUs and programming languages. So for example, you can do bitwise AND operations, you can do bitwise OR operations, adds and subtracts on these words, you can do exclusive OR operations, and those would all count as constant time operations. The things you could literally write as an expression in C++, Python, or TSQL. And this is also related to the external memory model, where you would have all of your memory being allocated in blocks on a disk, but your internal memory computations can be as sophisticated as you want and even operate on the bits if you want to. So in this more realistic model, Kopolowitz et al. In 2015 showed that you can have a set intersection data structure, and then they use it to list all the triangles in the graph G in time that's proportional to the number of edges, m, times the arboricity times a log squared W over W, plus a log W plus K, where K is the number of triangles in the output. And what we're able to show in this paper is that we can improve their bound by a logarithmic factor, get almost what would be the optimal speed up with words of size W and only be, a factor of log W off from what would be the optimal speed up over W. In fact, I think this is probably, in fact, a lower bound, but we're not able to improve that or prove that lower bound. And we also give an external memory algorithm that has a related running time. Okay. So the improvement that we achieve is based on the use of a number of data structures that have been gaining popularity, and then we come up with a new variation on this theme of data structures that is commonly referred to as cuckoo hashing or cuckoo hash tables. And the idea of cuckoo hash tables is also very simple. So all of our algorithms are going to be as simple as this, more or less. That in a cuckoo hash table, you have two random hash functions, a pair of random hash functions that map every element to two distinct locations in a table. And then you insert every one of your elements in one of those two locations. And so in this picture, I've got a table here where I've showed cat, pig, and dog. And then in gray, I showed the alternative places where cat, dog, and pig could have gone, but were not put in those locations. And then if you want to do an insertion, anytime you insert a new element into one of these cuckoo tables, you, much like the cuckoo bird, nests in somebody else's nests, you put your element into that cell, and you kick out the element that is there already. And then that element bounces out to somebody else, and then that kicks out somebody. Until finally, you keep going and going and going, until hopefully you find an empty nest and you put your element into that cell and it stays there. Now there's sometimes, as this table gets more and more full, where you could get stuck and you kind of create a cycle that keeps bouncing and bouncing and bouncing. And in that case, as Kershett will show in 2010, one way out of that dilemma is to also introduce a very small constant size cache they call the stash, where you can put elements into that would have otherwise caused this infinite loop bouncing to occur when you do an insert. And then the way you analyze these kind of algorithms is with respect to something called the cuckoo graph. This is strictly for the sake of the analysis, but you imagine that there's a graph where every one of the cells on your table is a node, and then you create an edge between two cells for every element that is then connecting the two places where it can go. And then they do some fancy analysis I'm not going to talk about to prove that if you have a stash of constant size, then your probability of failure for inserting n items is 1 over n to the s, where s is the size of that stash. All right, so now getting even more recent is this concept of a cuckoo filter. So a cuckoo filter is one of these now data structures that's going to take advantage of the word RAM model. The idea is that in addition to a standard cuckoo table, you also have a very small but parallel table where every cell on this table is now just a small little fingerprint that is constructed as a random hash function from the element. So cat could map to the fingerprint 2, pig would be mapped to 5, dog would be mapped to 4, and then you'd store those fingerprints in exactly the same place, position-wise, as you would find those same elements in the table. Okay? And then as a way to sort of indicate that these cells are full, you also can introduce a mask vector where you put 1s into the bits of a cell that's full and you put 0s into the bits of any cell that is empty. And this allows you to detect whether or not a cell is full or empty. Again, this is review, but more recent work. So in this paper, we introduce and study and then apply a variation on this theme that we call the 2-3 cuckoo filter. So in the 2-3 cuckoo filter, it's just like that model we had before, except now every element is going to be stored in 2 out of 3 possible locations. So we still have the one table, and now instead of 2 hash functions, we have 3 random hash functions that maps every element to 3 possible locations, distinct locations. And so we build a table that is this 2-3 cuckoo table. And in addition, we have a mask that will also show where every element goes. And then, just like before, we have a filter vector, which puts into a position in the corresponding location a fingerprint for every element. So in this picture I've showed in gray, again, what would be the 3rd location where each element goes, but every element is copied twice in that table. Okay? Now, in order to analyze this data structure, we introduce this concept of a cuckoo hypergraph, which is 3 uniform. That is, every hyperedge in this hypergraph has 3 vertices. And then hence this 2 out of 3 paradigm of choosing 2 out of 3 locations will correspond to a 2 assignment. That is more or less a matching of 2 out of the 3 vertices of every hyperedge in a way that is guaranteed to be disjoint. Again, the vertices in this case are cells in the cuckoo table, and then the hyperedges would be for every one of your elements, what are the 3 locations that that element would get mapped to. So exactly analogous to the cuckoo graph. And then we see sort of some possible structures that these kind of hypergraphs can form. In this first example here, this would be something that would be called unicyclic. It has exactly 1 cycle of hyperedges. And this would be an example of something that's acyclic. There's no cycle among the hyperedges. So then what we show is that 2-3 cuckoo tables have a 2 assignment, can be successful if and only if each of its connected components is either acyclic or unicyclic. And so this is exactly characterizing the cases when 2-3 cuckoo hashing can work. And then we show that if you just choose things at random, the way you'd get from a random hash function, then with high probability, the components, the connected components that you form in this cuckoo hypergraph are going to be small. And in the interest of time, I'm not going to go into those details. Similarly, there's a related concept of a cyclomatic number that is the smallest number of triangles which could be removed in order to create a graph to become acyclic. And this is now going to be also something that we bound to show that with high probability, you get that if you now use a stash where those acyclomatic elements would be going, that with high probability you can successfully build one of these 2-3 cuckoo tables. Okay? All right, so now that we've got the correctness behind us, talk about how we could use these 2-3 cuckoo filters to solve, say, a set intersection query. And the idea is basically to use this formula of simple bitwise operations, bit parallel operations on the words, defining one of these cuckoo filters, F, and using its mask, M, to go with it, to then, for 2 different filters, defined for 2 different sets, but with the same hash functions, to then compute this intersection. So here in this example, I've showed in a star all the locations where the filter would say we have an overlap and the fingerprints match in those 2 locations. And then the algorithm would just go through, and for every one of these elements where you have a match, you just go back to the original cuckoo table and make sure that those 2 elements really are matching. So that's got 2 cats. Yeah, that really is a part of the intersection. Here's 2 pigs. That's part of the intersection. Oh, here we have a dog, and we have a fox, and they both had a fingerprint of 4 and mapped to the same location. This would now be a false positive. And you'd say, okay, that's not part of the intersection. I double checked it, but sorry, that's a false positive. I'm not going to output that number. that element as belonging to the set intersection. It's a real simple algorithm. So in terms of the analysis, now that you have all this power of the 2-3 paradigm, real simple analysis says that the size of any of these, first we're going to succeed constructing these with high probability. And it wasn't an accident that we chose these fingerprints to have size log W bits, because if you have log W bits chosen at random, then false positives now are going to occur with probability less than 1 over W. And so the expected number of false positives is N over W, which is dominated by the running time it took you just to scan through all these words, do the bit parallel operations, and then extract out all the places where matches occurred. So the false positives get sort of washed away by this term, and then you have this K term where you're characterizing the number of actual intersections that you output. And then our triangle listing algorithm is exactly like the high-level algorithm we talked about before. First, orient all the edges according to a K degeneracy ordering, and then for every edge, use this set intersection algorithm to intersect the outgoing adjacency lists. And if you just add up the running times of all of those intersections, this is the bound that you get, which again improves the previous bound by a logarithmic factor. This is admittedly a theory paper. We're not going to apologize for that, but we nevertheless had an undergraduate do some preliminary experiments and showed that even with just a simple word size of 64 and using fingerprint size of 8, we can improve the running time from that simple-minded approach of Chiba Nishizaki from before to come up with even a faster algorithm in practice. And then, as I mentioned, we also have an external memory algorithm. It's in the paper. If you're interested in external memory, I'd urge you to look at that, where we have this model where you have an internal memory which has a certain size M. You have I/O operations against the disk, each of size B. And in that case, we get this number of I/Os that in the expected case would yield the number of I/Os in this bound here. So then to conclude, what we showed is that these 2-3 cuckoo hash filters are very simple and yet lead to improved algorithms for set intersection queries and then this triangle listing problem. We feel somehow intuitively that such a simple but powerful data structure should have other applications. So we leave as an open problem, are there other applications for these 2-3 hash filters? Thank you.
Any questions for the speaker?
Did you consider the application of the cuckoo hash filters to, say, relational joins that generalize the triangles?
We haven't explored that. That, I think, is an excellent idea. Last night as I was doing my slides, I was thinking about this a little bit, but it seems like in that case, if you have some more complicated formula, if you can put it into a conjunctive normal form, then each of the conjuncts could be done this way, and then you just have to union together all the results.
Sounds interesting.
But nobody has actually done that. That was just a vague idea I had last night.
Don't tell anyone.
Okay. It's our little secret.
A question on the external memory algorithm. Is this the best known algorithm in terms of aberrosity?
With respect to the external memory algorithms, there's two different PODS papers that come before this one that address a related problem, subtly different, called the triangle enumeration problem, where you don't actually output the triangles, you just call some kind of internal memory algorithm function.
Yeah.
And then You can like count them and do things like this.
Oh, okay.
And in those cases, you get, for those other previous algorithms, you get bounds that are very different than this.
Right.
And so it's for me, it's very hard to compare because it depends on what is M, what is this, what is this. So it depends on what the parameters are to say when this one is going to be better than those other ones.
Okay.
So it's not as easy to say this strictly beats them by some factor.
Okay. All right. Okay. And is M the number of edges?
Yes. Little m is number of edges here.
Okay. But then, do you consider how to encode the edges? No, but
Well, we still assume that the edges are just pairs of vertex labels.
right.
And that the
But then-
vertex labels are just numbers, let's say 1 to n, to keep life simple.
But then M over W, you cannot even read all the input, right? So I thought M should be the number of bits.
No.
Needed
M
to
is the
repeat.
number of elements. So even in this external memory model, you're still counting the number of, in this case, IOs of blocks of size capital B.
Okay.
But the number of elements inside B is counted in terms of words.
Okay.
So the total number of bits in every block is B times W.
oh, bits. So W is the number of words.
Yeah.
Okay. It's not
No,
bits.
W is the number of bits in a word. And what I'm not showing at all is this capital M and capital B. That's hidden in this
A sort.
this notation that we use in the external memory world. We
Okay.
just use sort as a
Okay.
symbolic shorthand for a running time that's capital N over capital B times the log base capital M over capital B
Okay.
of capital N over capital B. So it's
All
it's
right.
kind of this cumbersome thing, so we always just write it as sort.
Okay. Anyway.
I think we have another question, if there's time.
Yeah, maybe you can catch a flight.
It's okay.
A quick question. It's maybe a bit technical, but after you've computed the intersection, you need to iterate over all the places in the word where there was a match or a potential match.
That's correct.
So what is the machine operation, or are you sort of assuming a transdichotomous model or some crazy
No. So we use it's a standard operation, but I kind of skipped over that detail. But it's the most significant bit operation.
Okay. Got it.
So inside of Word, you assume you can immediately go to the most significant bit and then find that one. Then you can turn it off and go to the next one, turn that off. And so in time proportional to the number of bits, you can read off all the places where there's ones.
Thank you.
Yeah.
How do I?
Okay. All right. Thanks.
Hello? Yep. Okay. This one. Yeah. Yeah. Let's go back to the very first.
Oh.
The clicker that I use. And this is.
All right. So the next talk in this session is still on the triangle listing problem. Except that the graph this time is random, and DCR will give the talk.
Good afternoon. So, my talk is on asymptotic cost of triangle listing in random graphs instead of considering the problem in deterministic graphs. First, a brief introduction, which I assume the last speaker has already talked about, which is to identify all 3 node cycles inside a graph. There are numerous applications of the triangle listing problem, and using like network analysis, in like computing the cluster coefficient, and identify the transitivity, and in social networks to detect spams or community, and also using a lot of fields. But until today, there's also many problems that, for example, what's the impact of the distribution on the CPU cost, and how do we decide the best neighbor traversal order, and how do we find the optimal orientation pattern, and how do we compare different strategies, and how do we compare their asymptotic cost? And those are the problems that we're going to study in random graphs. So the background, the triangle listing, if implemented naively, is going to each node and to verify the age existence between each pair of neighbors. So for a simple example, using the star graph, like for example, if the star graph is 40 many nodes, and that's going to lead at least 800 trillion verification of the ages. So that's the amount of CPU cores that we are interested in studying. So there is a famous technique which is called cyclic orientation, which is to choose a direction for every age so that the resulting graph has no cycles. So for example, if we're going to orient this graph using descending orientation, which is to say that the nodes are going to ordered in descending order of the degrees, and the nodes with larger labels going to have ages pointing to nodes with smaller labels. So for example, like this. And when the graph is oriented, the triangle listing problem will now only involve checking among only out neighbors or in neighbors or a combination of these two. So since now we don't have any cycles in the graph, the age verification cost is 0, which is a huge improvement. So we summarize the relabeling and an orientation as a new term we call permutation, which is the first step is to shuffle the nodes using some universal order O, and then assign sequential labels from 1 to n to those nodes. And then we're going to direct ages from larger labels to smaller labels. Okay? And then the last step is going to list triangles using a fixed order, say x less than y less than z, which is only listed once, compared to implement naively, which is going to every triangle is visited 3 factorial, which is 6 times. So now after the orientation, let's say the node with a new ID I has its degree split into 2 parts. One is the out degree, we call it xi, and the other part is an in degree, which is yi, and they should sum to the original degree di. So we after analyzing all the methods, and we conclude that the CPU cost of all known methods can be expressed in such a formula, where m is a method we're going to use, theta n is a permutation on the permutation and orientation on the graph that we're going to use, and f is a function that depends only on m. So previous studies of the complexity of the triangle listing assume the graph has m ages, and until now the complexity is big O of m to the 1.5. Well, also that also holds for if the complexity expressed as m times arboricity of the graph, since the arboricity of the graph is only known to be 1 for planar graphs, but square root of m for other graphs. So that's basically m to the 1.5. And this bound, well, we say it is quite loose in sparse graphs and haven't improved in about 40 years. And also, it's still unclear how do we choose the best permutation and the best neighborhood traverse pattern to minimize the runtime. And the most important or the largest obstacle is that trying to minimize the cost function on a deterministic graph is likely a NP-hard problem. So instead, we seek an alternative path, which is to getting some more information using random graph models. And for some definitions, suppose fnx is a CDF of the degree distribution on a finite graph with, say, n nodes. And assume the series of fnx will converge finally to a semi-limit fx when n tends to infinity. And now, since this is a realm of random graphs, our concern is with the expected cost of graphs that realize, all graphs that realize a specific degree distribution. So there was actually a prior result. In 2015, Barberi obtained the cost for a particular method, only one method we call T1, and under only one permutation, which is descending degree. And this is a quite complicated formula where the Dn is the random degree sequence that the expectation is conditioned on, while there are, well, 4 random variables in this equation, z1 to d3 and d, they follow the same distribution effects. Though, if assuming Pareto degree distribution, they obtain the same finite condition, which is to say, this limit is a finite number when alpha is larger than 3.4/3. Well, the finite is saying that the cost is the per node cost. So it's not saying the total complexity is finite, but if it is normalized by number of nodes, the cost is finite. Okay, so though he obtained this result, the derivations and the formula is quite complicated, and it's not clear whether we can extend these results to other scenarios, since in our paper, we conclude that there are in total 18 traverse orders, and well, there are many permutations that we use. So the open issues are still which permutations or methods, like neighbor traversing patterns, are fundamentally better for a given degree distribution, and under what conditions. And the most important problem is that does the permutation and a specific traversing pattern improve the asymptotics of the big O notation, or just some constant inside the big O notation? So I'm going to first start with our unified framework, which we proposed and generalized from and subsumes all previous methods. In total 18, which can be classified into 3 categories. The first is called vertex iterator, which will check the neighbor pairs between each pair of nodes against the hash table over the whole graph. And the second is the scanning edge iterator, which is going to intersection the neighbor list of 2 nodes sequentially using 2 pointers. And of course, we assume that neighbor lists are sorted. So that's a fundamental and commonly known set intersection algorithm. And also there's another one called lookup edge iterator, which is to first build a hash table of the neighbor list of one node, and then for the neighbor list of another node, it is going to generate candidate edges and going to check against that hash table. But we identified that the lookup edge iterators have identical, it has no benefit of CPU cost over compared to vertex iterator, and it has higher I/O, so we're going to omit this category of algorithm from now on. Though it may seem that the order in which neighbors are visited does not make a difference to the complexity, but actually, after our analysis, they make a huge difference. And furthermore, the improvement is not just within the constants of the big O notation, but it is actually changing asymptotics of the big O notation. So a total of 18 distinct methods, but many of them have identical cost. For example, the method T1, if we reverse a permutation, by reversing the permutation, that means, for example, first the permutation is ascending degree permitted, and the reversion is just a descending degree permitted. So by reversing the permutation, T1 is identical to T3. Or if we just swap the order of the last 2 nodes visited, T1 is identical to T4. So after all this analysis, we identified that there are two equivalent classes within VI, vertex iterator. And also, we did the same thing for scanning age iterator and conclude that there are also two equivalent classes. So we're going to pick a representative from each class of each category, and that forms our four competing algorithms, the T1 and T2 and E1 and E4. The reason why we pick these four is that either it is the best out of its equivalence classes. Well, I mean, it should be the best of its own equivalent classes, but we cannot compare the representative from two equivalent classes till now. But we're going to address that later. So, as we know, the runtime of algorithm is, well, theoretically is the number of cores divided by the speed of the elementary speed. And for the vertex iterator and the lookup age iterator, they're both going to use hash tables. While for the scanning age iterator, it can use SIMD intersection instructions, which has a huge advantage of the speed over hash tables. It's like a factor of 100 times faster. So the question here is that the speed can be easily benchmarked, but what's the optimal cost for each method? Say, the scanning age iterator has a speed of elementary operation 100 times faster, but does it have 100 times more cost? So that's a point to compare. The one thing to note that E1 has strictly more operations than T1 and T2. And as a matter of fact, the cost of T1 is the summation of the cost of E1 is the summation of the cost of T1 and T2. But by how much? So that's what I'm going to address next. So our main results, the cost of 18 method can be summarized by a sum of functions of order statistics, where the gx is a universal fixed function for all methods, while hx is given by the table above and depends on the specific algorithm that you're going to use. For example, T1 is x squared divided by 2, and E1 is x times 2 minus divided by 2, which is different. And the qi depends on the permitted degree sequence, which tells the probability of the nodes of a node I that has smaller IDs than itself, which is to say, the ratio of its neighbor list being its R degree. So now, since the DI, the sequence is sorted, and which means it's, well, because in the ascending or in the descending permutation, it's either sorted ascendingly or descendingly. So that's not randomly scattered around the range from 1 to n, and that sum, which is the cost of the cost function, has some peculiar properties, but luckily, fortunately, this property is already studied by a field called L estimators, and we're going to directly use the results to obtain the closed form for our model. So it's stated as follows. For any method, when it's doing ascendingly permutation, it's going to converge to this closed form when n tends to infinity, and also for descending permutation, it's going to converge to this form, where this jx is the spread distribution of the degree distribution. Well, interestingly thing is that the jx specify the probability of one node when it's selecting its neighbor. The probability is biased towards the weight of larger weights. Well, in here, the weight is the degree of the nodes. In particular, we're going to obtain the closed form for our T1 method under descending permutation and the cost of E1 under the descending permutation, which we're going to show that that's the optimal permutation for these two specific algorithm, and that's what we're going to consider finally. So, however, we have obtained the cost of monotonic permutations like ascending or descending. Does there exist some other permutations like we shuffle the nodes randomly? Do they have better performance than the monotonic permutations? We're going to propose a new framework to analyze this. So suppose the permutation theta will converge to a random map of the function c of a number u, where the u is a number between 0 and 1, which tells the location of node I in relative to the range from 1 to n. So it's u equals to I divided by n. And this random map c specify the new location of the node I after the permutation, which is to say, what's its new label after permutation. So the conclusion we arrived at using this random map probabilistic is that the c function is applied to this j of z. And that's still a simple formula to look at. So the conclusion until here is that even though we can handle a much wider classes of permutations or methods all expressed in this simple form, the model and derivations are much more simpler than prior work. So armed with that previous result, this finally allows us to establish optimal permutation for certain families of algorithms. For example, T1 and E1 are both optimized by descending permutation, while T2 is optimized by round-robin permutation. The round-robin, which is to say, we're going to place larger nodes with larger degrees towards the outside of the range 1 to n. So, for example, the largest degree is going to be placed at location 1, and the second largest is going to be placed at location n, and so forth. And the algorithm E4 is optimized by complementary round-robin, which literally is a complement of round-robin, and is to place larger degrees towards the center of the range 1 to n. So next, our result is a comparison between the algorithm within each category of algorithms. Say, we're going to compare T1 and T2 within vertex iterator, and we're going to compare E1 and E4 within scanning age iterator. And the result is that T1 is better than T2 in limit cost for all degree distributions, and E1 is better than E4 for all cases. So finally, what's the result of comparing vertex iterator and scanning age iterator? Condition on we already have the best representative from their own category. So assuming Pareto degree distribution, which is commonly observed and used in real-world graphs, the cost of T1 per node cost is finite if alpha is larger than 4/3, which agrees with the result in the prior work. And the finite condition for E1 is alpha larger than 1.5. So consequently, this is saying that if the alpha falls into the range between 4/3 and 1.5, the T1 is always better than E1 in the limit of cost. But however, in real-world graphs, as we have experimented, the E1 has, well, roughly 2 to 3 more cost than T1, but has 100 times faster execution speed taking advantage of SIMD intersection instructions. So that's our final winner, which is E1. So a thing need to note that the derived limits are exact for all cases, but the numerical results, for example, at finite n, is only accurate for small n with graphs with constraint degree. So the constraint degree means the largest degree of a graph is constrained by square root of n, while for large n if the graph is not constrained, which is to say the largest degree can go up to n-1, the asymptotics numerically, when the asymptotic cost is finite, the numerical result is only accurate for large n, so it may exhibit quite a bit of error when n is small. Open issues still stand that when n is small and when the limit cost is infinite and when the degree distribution is unconstrained, the model is still not accurate. So in summary, the takeaway point is that both a permutation and a neighbor with order change the asymptotics of the big O notation, which is a huge improvement on modeling the CPU cost of triangle listing problem. And finally, our evaluation using some simulation graphs. And we can see here for constraint graphs, the error shrink monotonic to 0, and it's not very big when n is small. And for unconstrained graphs, the error could be big when n is small, but we can see its trend is shrinking monotonically because the cost is finite here. And finally, we have our experiments caused on a real graph, which is the Twitter graph used all in prior studies, which follows our prediction using the model, saying that the descending degree is optimal for T1 and E1, which is highlighted in gray here. When we compare horizontally, this is a small number for this algorithm. And round robin is optimal for T2, highlighted in gray here, and the best cost of E1 is double that of T2, as we can compute here, 255 times 2, roughly 510. Matches pretty well. So in the end, we have a column here, which is the degenerate permutation, which is, I think, is similar to what was proposed in the last presentation. It minimized the descending, minimized the cost of T1 under descending degree by a factor by roughly 10%, but it increased the cost of other 3 methods by a factor of 2 to 3 times. So we claim it's not comparable, and also we cannot obtain any use for information, general information from this. Thank you.
Any questions for the speaker? Okay. Okay, let's thank the speaker again.
Thank you. Oh, yeah. Sorry.
So the next talk is efficiently enumerating minimal triangulations.
I think it was both. Here it is.
This one?
This one. Yes, this one.
And Nova will give a talk.
Hello. Do you hear me? So my work will be on, the work I'm presenting is about enumerating minimal triangulations, which is not exactly triangles, which is what we saw up until now. This is a joint work with Benny Kimmelfeld and Batya Kenny. So I will start by explaining the motivation, which is 3D compositions. So why do we need 3D compositions? Why do we want to enumerate them? And why does it mean that we want to enumerate the minimal triangulations? And then I will go over to the theoretical part, which is the algorithm we suggest and the complexity guarantees it gives. And then I will go over to the practical part, which is the implementation we did and the experiments we ran. So let's start with the motivation. So I'll go over this part quite quickly. Why do we need 3D compositions? So assume we're interested in evaluating a conjunctive query. This is an example. We can consider the graph that corresponds to this query. So in this graph, every node is an attribute, and 2 nodes are connected by an edge if the attributes appear in the same relation. And this is another conjunctive query with the graph that corresponds to that. So evaluating a general conjunctive query is a hard problem, but if we have an acyclic query like the first one, then there is an efficient algorithm to solve this problem. Unfortunately, not all interesting queries are acyclic. So what do we do when we have cyclic queries? This is exactly where we would want to use tree decompositions. So tree decompositions extract some tree structure out of the graph, and it allows us to use the efficient algorithm for cyclic graphs. So in more details, if this is the graph of interest, this is a tree decomposition of this graph. So it's a tree where every node is a bag that represents a subset of nodes of the original graph. It needs to contain the entire original graph, and we want every node of the original graph to appear in a connected part of this tree. The way you would usually use a tree decomposition is you would run the general algorithm on each one of the bags separately, and then you would combine the results together using the efficient algorithm that only works for acyclic graphs. So usually, when you use the tree decomposition, the runtime is exponential in the size of the largest bag. Now, for those of you who know, sometimes when we talk about queries like the example I gave, and if we have relations that are not binary, then we're interested in generalized hypertree decompositions. I will not talk about them, but generalized hypertree decompositions entail some tree decompositions. So we can find the tree decompositions, then use them to find generalized hypertree decompositions. I will concentrate on the part of finding the tree decompositions. So this was just an example. Tree decompositions have many other applications in different fields, and I will mention probabilistic graphical models when we get to the experiment section. So we're convinced we want to use a tree decomposition, but how do we know which one to use? A graph can have many tree decompositions, and this is an example. So the common thing to do today is to try to minimize the width, which means that we want the largest bag to be as small as possible. But unfortunately, finding the smallest width is a hard problem. So what we usually do today is that we use heuristics to find a pretty good tree decomposition with a pretty good width. But even if we can get pretty good width, width isn't always everything we're looking for. This is an example of work presented in EDBT this year. It's about join optimization using caching. So here you can see that this is from their experimental section, and then they use their algorithm using two different tree decompositions. And even though those decompositions are isomorphic, not only they have the same width, they're isomorphic, one of them runs 100 times faster than the other one. This is because different attributes can be better for caching, like country is better for caching than user ID. So what I'm trying to say is that different applications have different requirements of the tree decompositions other than the width. So what we would like is we would like to find tree decompositions with low width, and we would also like to find many of them. So we can choose between them according to our application. And this brings the approach of enumeration that we see in recent work. This is a work done in Stanford about generalized hypertree decompositions. And what they suggest is to generate all the generalized hypertree decompositions, calculate some measure to see which one is best, and then choose the best one. But the way they suggest doing this gives no complexity guarantees, and it works for small graphs, which is what they assume they have. But we would like to find a solution which is practical for even larger graphs. This is a work done in Vienna and presented in IJKAI. It's about using machine learning to choose between a pool of tree decompositions. And what they do in their experiment section is that they generate a pool using different heuristics, and then they show how to choose between the decompositions in this pool. But of course, maybe there are better decompositions that are not in this pool, and we would like to generate them as well. So this is our question. Can we enumerate the tree decompositions, and can we do that with efficiency guarantees? So our goal is to enumerate all tree decompositions We would like the solution to provide complexity guarantees, and we also want the solution to be efficient in practice. Now, do we really want to enumerate all 3D compositions? If we're only devising an algorithm to find one 3D composition, which is pretty good, we know we will get a good result. But if we're talking about returning all of them, then we need to be more specific by saying what can be an interesting 3D composition. We don't want to waste time about generating things that are not interested. In particular, if you have a graph that is already a tree, the only 3D compositions that make sense is that every bag has only one node. So it's basically the graph itself. More specifically, this is an example of a graph, and this is a valid 3D composition of this graph. But the whole point of a 3D composition is to decompose. So if we can decompose it further, we would like to do that. And this is a better 3D composition. And we can get an even better 3D composition because the bottom bag is contained in the middle one. So we can just remove it all together and get a smaller 3D composition. So if we can generate the last 3D composition here, we're not interested in the previous ones because this is better. So we defined the notion of proper 3D compositions, and intuitively what it means is that they cannot be improved by removing or splitting a bag. So our goal now is to enumerate all the proper 3D compositions of a graph. And of course with complexity guarantees, and we want the solution to be efficient in practice. Now, there can be exponentially many proper 3D compositions. So only printing them may take exponential time. So what is an efficient algorithm? This is where we use standard measures for complexity of enumeration. One of them is polynomial delay. So this measure says that the delay between every two answers is polynomial in the size of the input. And another standard measure is incremental polynomial time. So it's similar, but as time goes by, we allow the algorithm to take more time before it returns more results. So the delay before answer I is polynomial in the size of the input plus I. And our result is that we can enumerate the proper 3D compositions in incremental polynomial time. Now, the way we do that is that we show a bijection to minimal triangulations. I will say what it is in a moment. And then we show how to find the minimal triangulations in incremental polynomial time. So now we want to understand what are minimal triangulations, how does this help us enumerating the proper 3D compositions, and how can we enumerate them. So if this is the graph of interest, these are its two minimal triangulations. A triangulation is when you add edges to the graph to make it chordal. So a chordal graph is a graph where every cycle of length 4 or more has an edge crossing it. So here we had a cycle of length 4, and we had two options of how to add an edge crossing this cycle. It's minimal in the sense that you cannot just add a subset of these edges and still get a chordal graph. So given the minimal triangulations, so the minimal triangulations are chordal graphs, and it's easy to find the proper 3D compositions of chordal graphs. For those of you who are interested in more details, so the bags are the maximal clicks, and the edges, you choose where to put the edges by a maximal spanning tree, where the weight is the size of the intersection of the bags. But anyway, so given a minimal triangulation, it's easy to find the proper 3D compositions. And what we show is the bijection saying that these proper 3D compositions are exactly the proper 3D compositions of the original graph. So there is a bijection between the minimal triangulations and equivalence classes of proper 3D compositions. So if we can enumerate the minimal triangulations, we can easily find all the proper 3D compositions. Now, what we want to do now is just to enumerate the minimal triangulations. And there is a known bijection between minimal triangulations and maximal independent sets. So this is a separator graph of the original graph. What this graph has is that every node is a minimal separator, which is a subset of nodes that if you remove them, you separate the graph to components. And two separators are connected by an edge if the separators are crossing, which means that they separate each other. So the bijection says that the maximal independence sets on the separator graphs corresponds to minimal triangulations. And again, more details for those of you who are interested. The way the bijection works is that if you choose a minimal separator and two nodes in there don't share an edge, you just add this edge. So to enumerate the minimal triangulations, all we need to do is to enumerate maximal independent sets on this separator graph. And enumerating maximal independent sets can be done in polynomial delay. So that's great. Are we done? Well, not really. The maximal independent sets are on the separators graph, not on the original graph. And the separators graph can be of exponential size. This is an example. So we can't really generate this separator graph and then run some algorithm and then still expect to get the first result after polynomial time. So what we want to do here is we want to find the maximal independent sets of a graph we cannot even generate. And this is what the algorithm that we propose does. So it's a redesign of an algorithm for hereditary graph properties by Cohen et al. And of course, we need some assumptions to be able to do that. So we want to be able to enumerate the nodes in polynomial delay. We want to be able to check whether an edge exists between two nodes in polynomial time. We want the size of every maximal independent set to be polynomial. So there can be exponentially many nodes, but the size of every maximal independent set is polynomial. And we want to be able to extend an independent set to a maximal independent set in polynomial time. And I will say a few words more about that. So these are all things we can do in the case of the separator graph. So this is why we can apply this algorithm to find the minimal triangulations. Now, one thing I want to say about our algorithm is that it has these steps of extending an independent set to a maximal independent set. Now, as we said, maximal independent sets correspond to minimal triangulations. So in fact, we can take any method of minimal triangulation or even 3D composition, and we can use it for these steps of extending an independent set. So what we do here, we start by extending the empty set, which just basically means take a method for minimal triangulation, run it on your original graph, and return the results. And then we extend other sets. So we just use the same method on different graphs, and we get more minimal triangulations of our original graph. So this algorithm doesn't replace existing methods. It uses them, and it tries to get more results using the same method. So this is a summary of the solution. To enumerate the proper 3D compositions, we enumerate the minimal triangulations. And for that, we want to enumerate the maximal independent sets of a graph we cannot generate. And we can do this given that we can find a single minimal triangulation, and we know how to do that. So this is the theoretical part, but we want to know, can we actually use this algorithm in practice? And how good are the results? Does it maybe even improve on standard measures? So we implemented it with C++. The code is online. There's a link in our paper if you're interested. We used standard triangulation algorithms for the steps of extending an independent set, maximal cardinality search and min field. And we used graphs from real data in different fields. One of them is database queries. For this, we used the TPCH data sets, and we used the translation of these queries to conjunctive queries given to us by logic blocks. And another field is probabilistic graphical models. For this, we used graphs from the UAI Inference Challenge. So in some cases, the graph is small and there are not many results, and we can return all of them in reasonable time. But in some other cases, as we said, there can be very many results. So in these cases, we won't really let the algorithm, the run terminate. We'll just run this for whatever we think is reasonable and stop, and then take the best we saw so far. So we use it as an anytime algorithm to try to improve a method and get better results. So this is an example of one of these graphs that takes too long. And we see what we can get in 30 minutes. So the purple line is all the results we got. So in 30 minutes, we got more than 4,000 results. The second chart talks about the measure. So the first minimal triangulations we got had width 46, and then quite quickly we could improve the width and find a triangulation with a lower width of 39. You can see that there is also a significant improvement in the fill, which is another standard measure I didn't mention. So we know we have a lot of results, and we know that we can improve on measures, but how many of the results are good? Do we have just one, or do we have a lot? So we checked that as well. And the green line is the number of results which are at least as good as the first result, the one we would get by just applying the method, in terms of width. And the red line is the number of results with the minimal width we could find. So that's results with width 39. For the graphs, for the graph queries, for the query graphs, these are the results. So we could find all the minimal triangulations of all the graphs in this data set within 5 seconds. Most of the graphs were already triangulated, and 2 graphs had hundreds of minimal triangulation. Now, we wanted to compare a runtime against something that exists, but we don't know of any algorithm for finding minimal triangulations or proper tree decompositions. What we do know is of an algorithm for finding generalized hypertree decompositions. I mentioned that earlier. And this entails some tree decomposition. So if we want to compare against something, we can take the tree decompositions that are generated by these generalized hypertree decompositions and try to compare against that. But when we tried to run this algorithm against the same data set, we couldn't get it to finish against with some of the larger graphs here. And this is for the larger graphs. So these are graphs from the probabilistic graphical models, and these are aggregated results. So here it's aggregated among all the graphs that the run didn't finish in 30 minutes. So what does it mean? Let's look at the first row here. What happened when we used maximal cardinality search as the method, and we're interested in the width as the measure. So we got 30,000 results on average. About a third of them had width which is at least as good as the first result. The average percent of improvement in the width was 2.6. But actually, for some results, we couldn't get any improvement at all because maybe even all the results had the same width. But for some other graphs, we could get a very high percent of improvement of a quarter. Now, if you remember, I said when we use tree decompositions, the time is exponential in the size of the width. So every small improvement in the width is very good for us. And for the fill, you can see that there is also a pretty significant improvement. Okay, so a few words about the direction for future work. On the theoretical side, we provided an algorithm with incremental polynomial time. So we still don't know if we can do that with polynomial delay.
Okay, any questions? So maybe I missed this part. So how do you compare two triangulations, and which one is better?
So this really depends on the application. So different applications can have different needs for what an
Can you give an example? Just to get a feeling of how things are done.
Well, I can't really give a simple example.
Maybe it then.
Yeah, I mean width, of course.
Well, widths are
Yes,
the
but a
smallest, right?
composition with the
Same width, yeah. How do you?
So, okay, so I'll go back to. Okay, so. No, that's not okay. There was some example for a work. Attributes in the adhesions. But it's only one specific application.
Depends on some other information than the graphs itself. Yeah, okay.
In this
Okay.
case.
Okay. All right. Any other questions?
They use the machine learning algorithm to learn the cost of a tree decomposition based on the problem at hand. And they looked at all sorts of graph optimization problems. So this is a learned function.
So the next talk is counting and enumerating database repairs.
Okay, so I'm going to present our work on counting and enumerating preferred database repairs. This is a joint work with Benny Kimmelfeld. So we're talking about inconsistent databases, where an inconsistent database is a database that violates some of the constraints assumed to hold. So what you see here is real data taken from DBpedia, a project that extracts structured data from Wikipedia. And you can see that this data is actually inconsistent because every person in this table has 2 different birthplaces, which is obviously not possible. And inconsistency may arise in many different situations. For example, when we're integrating data from different data sources, or if the data that we're using is imprecise, or if our data collecting process is imprecise, and so on. So there are 2 main approaches to handling inconsistency. The first one is database cleaning, where the goal is to clean the database, to remove the inconsistencies, and to have just one good repair of the inconsistent database. And the second approach is that of consistent query answering, where we do not clean the database remains inconsistent. However, for each query, we only want to return the answers that are not affected by inconsistency. And what that means is that we only want to return the answers that will appear in every possible repair of that inconsistent database. And to understand this, we must define a repair. So we consider subset repairs. And a subset repair is a sub-instance of the inconsistent one that is first of all consistent, and second, it's maximal. Okay, we cannot add any more facts without violating consistency. So if we go back to our example, then any repair of that inconsistent database will just have one birthplace for each person, right? So we can remove these facts and get one possible repair of the inconsistent database. And we can also remove these facts and get another possible repair of the same inconsistent database. So every inconsistent database may have many possible repairs. And if we want, for example, to return the consistent answers, then we must consider all of them. Right? And that's where preferences come into the picture. So in traditional data repairing, all of the repairs are equally good. And that's why we have to consider all of them. However, there are cases where we may prefer one repair over another one. Okay, and it may be the case, for example, when we're integrating data from different data sources and we consider one of them more reliable than another one. Another example is when we have timestamps and we prefer the most recent data, okay, and so on. So in this work, we focus on a framework proposed by Starocco et al. That incorporates preferences among facts in the database. What they proposed is to have a preference relation between conflicting facts. Okay, so we say that fact 1 is greater than fact 2 if fact 1 is preferred to fact 2 for some reason. Fagin et al. Showed that this framework actually captures some cleaning policies that are used in existing systems for text analytics, such as System T and Gate and others. So we now have preferences among facts in the database. But what we really want to have is preferences among repairs, because then instead of considering all of the possible repairs, we'll only have to consider the best ones, the most preferred ones. So the next question is, how do we leave the preferences among facts to preferences among repairs? And Starocco et al. Proposed 3 different notions of preferred repairs: globally optimal repairs, Pareto optimal repairs, and greedy or completion optimal repairs. So the first 2 notions are based on checking if a set of facts can be improved by a better set of facts. Okay, so suppose that we have 2 different repairs of the same inconsistent database. The blue facts appear in both of them, the red facts appear only on the right one, and the green facts appear only on the left one. So we say that the right one is a global improvement of the left one if for each green fact there exists a red fact that is preferred to it. Okay, so in this case we replace a set of facts with another set of facts such that each removed fact is preferred to by some inserted fact. Okay, so that's a global improvement. We say that the right one is a Pareto improvement of the left one if there exists one red fact that is preferred to all of the green ones. Okay, so in this case, we again replace a set of facts with another set of facts, but now one inserted fact is preferred to all of the removed ones. Okay, and that's a Pareto improvement. Then we say that a consistent sub-instance is a globally optimal repair if it does not have any global improvement. And it is a Pareto optimal repair if it does not have any Pareto improvement. The last notion of greedy repairs is based on this greedy algorithm for generating repairs. And what it basically does is it goes over the facts in the database by decreasing priority order. And for each fact, if it can be added to the repair without violating consistency, then it is added to the repair. Otherwise, it is just removed. And note that there can be many possible decreasing priority orders. And for each such order, the final result may be different. So all of the possible results of this algorithm are precisely the greedy repairs. Okay, and they're also called completion optimal repairs because there is an equivalent definition for greedy repairs that is based on a completion of the preference relation into a total order between conflicting facts, but I'll skip that definition because we will not use it. Okay, so all of the computational problems related to repairs are still relevant in this framework. For example, the problem of consistent query answering that was studied by Starocco et al. Another example is the problem of repair checking. Is a given sub-instance an optimal repair? This problem was also studied by Starocco et al. And then Fagin et al. Completed the dichotomy for globally optimal repairs. But now imagine that we have a system for data repairing that is based on this framework. Okay, so the first thing that we would like to know is when we're done. Right, so the first question that we want to be able to answer is there precisely one optimal repair? Because if there is precisely one optimal repair, then the given preferences suffice to clean the database unambiguously, and we can just use this one optimal repair to clean the data. Okay, so this problem is the problem of ambiguity, also called categoricity, and we have studied this problem in a previous work. But what if that's not the case? What if we have more than a single optimal repair? Then we would still like to have some indication to how far away we are from a single optimal repair. So the next question that we want to answer is, how many optimal repairs are there? Okay, and this is the problem of counting repairs, which is the first problem that we study in this work. But as I'll show you in a few minutes, counting is a hard problem in many cases. But even if counting is a hard problem, it still doesn't mean that we cannot answer questions like, are there at least 1,000 optimal repairs, or 100, or any polynomial number of optimal repairs? And if we had an algorithm for efficiently enumerating the repairs, generating them, then we could answer this question. So the problem of enumerating the repairs is the second problem that we study in this work. So let's start with the first problem. So the problem of counting the subset repairs, the traditional ones without preferences, was still an open problem. So we actually had to start with the more simple case of counting the number of subset repairs, and only then we moved on to the problem of counting the number of optimal repairs for all three notions of optimality proposed by Starocco et al. Okay, and note that we only consider schemas where the constraints are functional dependencies. Okay, so let's start with counting the subset repairs. So the problem of counting the subset repairs is actually equivalent to the problem of counting the number of maximal independent sets of the conflict graph. Okay, now the conflict graph is a graph that has a node for each fact in the database, and it has an edge between two nodes if the corresponding two facts violate some constraint. So in our example, we have two conflicting facts, a person that was born in two different places. So in the conflict graph, we will have a node for each one of these facts, and we will have an edge between them because they're conflicting facts. Okay? Now, every subset repair is a maximal independent set of that conflict graph, right? Because we want it to be independent, because we don't want edges, because we don't want conflicts in our repair. And since we define the repair as a maximal consistent subinstance, we want the maximal independent sets. So we basically just have to count the number of maximal independent sets in the conflict graph. The problem is counting the maximal independent sets of a given graph is known to be a hard problem. However, there are types of graphs for which we can count the number of maximal independent sets in polynomial time, and one of these tractable cases is the class of P4 free graphs. Okay? Now, a P4 free graph, also called cograph, is a graph that does not have any induced subgraph, which is a path of length 4. So this, for example, is not a P4 free graph, because you can see that this set of 4 nodes is exactly a path of length 4. So there exists a polynomial time algorithm for counting the number of maximal independent sets for P4 free graphs. And why are we interested in P4 free graphs? Because interestingly, the class of P4 free graphs captures precisely the cases where counting the number of subset repairs can be done in polynomial time. Again, what we have is the following dichotomy in data complexity for counting subset repairs. So suppose that we have a schema with functional dependencies, then counting the number of subset repairs can be done in polynomial time if and only if, for every instance over the schema, the conflict graph is a P4 free graph. Okay, and we can actually decide if this is the case, if these conditions hold, in polynomial time for every given schema. Now, when does this actually happen? When it is true that for every instance over the schema, the conflict graph is a P4free graph. So to understand this, we need a new definition. And this definition is a chain. Now, a chain is a very simple definition. Okay, we say that a set of functional dependencies is a chain if the left-hand sides of the functional dependencies in the set form a chain. So, for example, the left set of functional dependencies is a chain because you can see that B is contained in BC and BC is contained in BCF, right? So the left-hand sides of the functional dependencies form a chain. So if this is the set of functional dependencies in the schema, then we have a polynomial time algorithm for counting the number of subset repairs. The other set of functional dependencies is not a chain because you can see that BCG is not contained in BCF and BCF is not contained in BCG. So if this is the set of functional dependencies in the schema, then the problem of counting the number of subset repairs is sharply complete. Okay, and this is what we actually showed. We showed that for every instance I over the schema, the conflict graph is a P4free graph, if and only if the set of functional dependencies in the schema is equivalent to a chain set of functional dependencies. Okay, so this is what we have so far. Note that a single functional dependency is always a chain. So in the case of a single functional dependency, we have a polynomial time algorithm for counting the number of subset repairs. If we have a chain set of functional dependencies, then it's also polynomial. In any other case, the problem is sharply complete. And the next question is, what happens when we add preferences to the picture? So for optimal repairs, we have the following dichotomy that holds for all three notions of optimality. Okay, it's the same result. So in this case, again, suppose that we have a schema with functional dependencies, then counting the number of optimal repairs can be done in polynomial time, if and only if the restriction of the set of functional dependencies to any relation of the schema is equivalent to a single functional dependency. Okay, and actually the algorithm that we have for counting the number of optimal repairs in the case of a single functional dependency is very, very simple. And it turns out that this simple algorithm covers all of the tractable cases for optimal repairs. Okay, so this is the full picture that we have. Single functional dependency, always polynomial. A chain of functional dependencies, polynomial for subset repairs, and the sharply complete for optimal repairs, and any other case, sharply complete for both subset repairs and optimal repairs. So you can see that counting the number of repairs is actually a hard problem in most cases. But as I said before, it still doesn't mean that we cannot answer questions like, are there at least 100 optimal repairs? So now let's move on to the second problem that we studied in this paper, which is the problem of enumerating the repairs, generating them. So the problem of enumerating the subset repairs is again equivalent to the problem of enumerating the maximal independent sets of the conflict graph. Okay, and as Nofar mentioned before, there is an existing algorithm for enumerating the maximal independent sets of a given graph with polynomial delay, right? When the time between two consecutive answers is polynomial in the size of the input. So this problem is basically solved. For globally optimal repairs and Pareto optimal repairs, the two notions that are based on checking if a set of facts can be improved by a better set of facts, previous results on the ambiguity problem, the problem of deciding if there is precisely one optimal repair, imply that there is an efficient enumeration algorithm only in the case of a single functional dependency. And again, this algorithm is very, very simple. So the only question left is, can we enumerate the greedy repairs efficiently? Okay, the greedy repairs are those that can be generated using the greedy algorithm that I showed you before. And this is the result that we have for greedy repairs. So enumerating the greedy repairs can be done with polynomial delay for any set of functional dependencies and actually for any conflict graph. Okay, because conflict graphs can represent not only functional dependencies, but any constraint that is defined over pairs of facts. Now, many enumeration algorithms are based on the algorithm for enumerating the maximal independent sets of a graph, but it doesn't work very well in our case because the correctness of the algorithm for enumerating the maximal independent sets relies on the fact that every independent set can be extended to a maximal independent set, and just by adding more nodes. And it works for subset repairs because any consistent set of facts can be extended to a subset repair, again, just by adding more facts. So if we could use a similar algorithm if any consistent set of facts could be extended to a greedy repair. But this is not the case. Again, we actually showed that it is a hard problem to even decide if a given set of facts belongs to any greedy repair. So our algorithm still builds upon the algorithm for enumerating the maximal independent sets, but we have some non-trivial adjustment for greedy repairs. Okay. Finally, I want to show you another interesting result that we have in this paper, which holds in the case where the preference relation behaves as if determined by a confidence score. So in this case, we basically assume that each fact in the database is associated with some confidence score, okay, that can represent the reliability of the source of the data if we integrate the data from different sources, or the currency of the fact if we have timestamps, and so on. Okay, so in this example, we have the first two facts that are conflicting facts. The first fact has a confidence score of 3. The second fact has a confidence score of 6. So the second fact is preferred to the first fact. Okay, that's basically the idea. Now, if this is the case, if the preference relation behaves as if determined by a confidence score, then first of all three notions of optimality coincide. Okay, they become exactly the same. So any Pareto optimal repair is also a greedy repair, and every greedy repair is also a globally optimal repair, and so on. Second, in this case, we have another enumeration algorithm for enumerating the optimal repairs for all three notions in incremental polynomial time, okay, where the time between two consecutive answers is polynomial in the size of the input and in the number of results generated so far, for any conflict hypergraph of bounded dimension. Now, conflict hypergraphs are just a generalization of conflict graphs, and the important thing is that conflict hypergraphs of bounded dimension can represent many different types of constraints. Okay, they can represent functional dependencies and conditional functional dependencies, and equality generating dependencies, and the more general denial constraints, and so on. So in this case, we actually cover all of these types of constraints. So to conclude, in this work, we studied two problems. Okay, the first problem is that of counting the number of subset repairs and optimal repairs. The second problem is that of enumerating the repairs. Now, actually, one of the motivations behind preferred repairs was to reduce the space of repairs. Okay, because in some cases, the preferences may reduce the space of repairs so much compared to subset repairs that we can maybe even just store all of them explicitly. And then we could answer questions like consistent query answering efficiently. Okay, but even if there are only a few optimal repairs, it still doesn't mean that we can efficiently generate all of them. Right? So in this work, we have actually resolved this problem. Thank you.
Okay, thanks. So in case you have multiple repairs, so suppose I actually want to have a single repair. So wouldn't it, to measure kind of how far away you are from having a single repair, wouldn't it be kind of more intuitive to actually measure the amount of additional preference information that you would need to get a single repair, instead of giving like your 20,000 repairs? Because that's actually what the user would like to see, you know. It's like, so how this would be an alternative measure of actually, you know, measuring the deviation from having a single repair in the end. Did you think about this, or is this related somehow to what you have been doing?
So you're right, it is interesting to check how much preference information you need to get to a single optimal repair. But counting the number of repairs can also help you, because if, for example, you now have 100 repairs, and then you add one more preference, and now you have only 10, then you can see like how this preference helped you to get to a single optimal repair. But yes, it is interesting to check how much information you need to, yeah.
In the cases where you have Sharpie completeness, right? Once you have one Sharpie completeness, one usually try to have at least some approximation, right? One of these fully polynomial randomized approximation schemes, right? For the case of maximal independent set, that's not possible, right? It's proof, right? That unless BBP is contained in P. But for the cases where you have these change functional dependencies, right? Where you don't have general graph, it could be the case that you could have these approximations, right? Have you thought about that? No.
Well, we didn't think about it, but it's actually one of our directions for future work, to see if there is an approximation of the number of repairs, yes.
In case of changes, you can compute it precisely.
Yes.
When there are no changes, I mean, there can be a richer, like a trichotomy. That computation approximable, but shall be complete, and shall be complete a little possible. Yes. Yeah, you can do it over trichotomy.
Okay, thanks. Yeah, so this is joint work with my colleagues Jens Keppeler and Nicole Schweikart from Berlin. And we study the problem of evaluating conjunctive queries under database updates. And the setting is the following. So we consider relational databases as usual, where we assume that there is an infinite domain. And throughout the talk, I will use little n as the size of the active domain of the database. And we consider conjunctive queries, meaning conjunctions of relations, existential quantifiers, and possible free variables. And we want to evaluate these queries under updates, where updates are single tuple updates of the database, so insertions or deletions of single tuples. Yeah. And what means answering conjunctive queries? So we look at three kinds of query evaluation, first answering just Boolean queries, counting the number of result tuples, or, and that's why the talk is in this session, enumerating the result with constant delay between the tuples. So here, when I mean constant, I mean data complexity, so the size of the query is regarded as a constant. And yeah, and the task is that after every update, we want to report the new query result efficiently, so quickly. And what does this mean? So we say that we want to have constant update time, ideally, or polylogarithmic update time. So after constant update time, ideally, we want to report the new query result. And yeah, that sounds very ambitious, and it is. So first note that yeah, we want to characterize those queries that are efficient, that have efficient update time. And if you want to compare it with just the static time of evaluating a conjunctive queries, there is only a linear factor of difference. So because we could just insert all tuples of the database in the database and then use a dynamic algorithm to evaluate it in the static setting. And this in particular implies that if you want to have constant update time, then the query has linear data complexity. And this excludes, for example, triangle queries we have seen earlier in the session, or queries of bounded tree widths. So we are really very restricted. So one might argue, why do we have these restrictions? Well, at some point, at some sense, constant update time is something nice to have. On the other hand, if we would have studied, say, FPT or polynomial update time, this would have been just the same as analyzing what's the static time of evaluating conjunctive queries, and there's a lot of work that has already done this for the case of Boolean conjunctive queries, counting or enumerating conjunctive queries. And in all these cases, tree width always plays a crucial role in order to characterize efficient conjunctive queries that can be evaluated efficiently. And one contribution of our work is that we identify another measure that characterizes the efficiency of evaluating conjunctive queries under updates. So we examine a new class, so a fragment of conjunctive queries that allow constant update time. So for every conjunctive query that has a specific form that we call Q hierarchical, there is a dynamic data structure that has constant update time and allows all three task dimensions, so answering a Boolean conjunctive query, counting the number of result tuples, or start an enumeration of the result relation with constant delay between each tuple. So what are these Q hierarchical queries? So let's start with a very simple example. So the query just stating that there is a triple X, Y, and Z in a directed graph where X is a red node and Y is a green neighbor and F is a blue neighbor in this graph. So, and we can count just the number of occurrences of these patterns efficiently. So the number of occurrences is just the sum over all red vertices. And then we multiply the number of outgoing neighbors with relation E with the number of outgoing neighbors with relation F. And then this is the number of result tuples, so the number of occurrences of this pattern in a directed graph. And this can be done also efficiently after, can be maintained with constant update time, because if we store the number of outgoing neighbors with respect to the relations E and F, as well as our result, then we can update these numbers in constant time if we have random access to the data structure. So if we, for example, insert a green edge, then the out degree of only one vertex changes. So this can be done in constant time. Similarly, if we have want to enumerate the number of patterns that occur in the graph and look like this, then we could just store the adjacency list with respect to these relations E and F. in such a way that we have can in constant time insert and delete edges from these lists. And then in order to enumerate, we just go over all red vertices and then build the Cartesian product between all neighbors with respect to E and all neighbors with respect to F with a nested loop. So this gives us an enumeration with constant delay, and this can also be updated in constant time, assuming we have constant access to the relations. And this idea generalizes to queries where the query graph looks like this. And this gives us directly the definition of Q-hierarchical queries. So let's assume that we have such a tree where the vertices of the tree correspond to the variables of the query. And such a Q tree has the following property, namely that every relation symbol occurring in the query forms a directed path in this tree that starts at the root. And this is just the definition of hierarchical queries that occurred, for example, in the setting of probabilistic databases and characterized tractable queries there. One additional thing that we require is a requirement on the existential quantifiers, and we say that the free variables have to form a connected subtree of this tree that contains the root, meaning that whenever we have an existentially quantified variable, all variables in the subtree starting at this variable are also existentially quantified. So if a query has such a Q tree with these two properties, then we say that's Q hierarchical. And for these kind of queries, we are able to propagate this simple idea from above and design a data structure that allows efficient enumeration, counting, and answering Boolean queries. So, for example, if we have this Q hierarchical tree without any existential quantifiers, then our data structure is some kind of a factorized representation of the query result. So it somewhat mimics the tree structure of this query tree. And this allows to, for example, to enumerate all tuples with constant delay. So we instantiate X with some value A, Y with some value E, and Z prime, for example, with all possible values that build tuples. And then we can pass through these lists and on the same level build the Cartesian product and enumerate all tuples. So this is just so-called F representation of the query result. So the query result might be of large size, say n to the k, and this representation is only linear in the size of the database. So one additional thing we have to take care of that we do not only encode all tuples that are in the result relation into this data structure, but also do this for parts of the query that are not actually present in the query output. For example, if we have tuples in the relation R and S, say BPA, BPB, BPC, and so on, but we do not have the tuple EBP, then we know that this thing is not part of our query result yet, but we also represent it like here, but it's not connected to our original data structure. And if we now insert the relation EBP, then this gets part to our data structure. So the output of our query result increases to a large extent. But we are sure that if we merge these representations, then we now can, within constant time, start a new enumeration of the new query result that might be way larger. Okay, so this is the upper bound. So if a query is Q hierarchical, we have these simple algorithms that enumerates the query result. And our two main theorems are dichotomy theorems that actually these Q hierarchical queries, this property is optimal. So, for example, if we consider the task of counting the number of result tuples, our theorem states the following. So let Q be a fixed conjunctive query. Either Q is phi, the query phi is equivalent to a Q hierarchical query, then we can compute the query result with constant update time. And if it's not equivalent to a query hierarchical query, then we cannot compute the query result with truly sublinear update time in the size of the active domain. So, and of course, we have to assume some conjectures, and the conjectures we assume here are the orthogonal vectors conjecture and the online matrix vector multiplication conjecture. So, two conjectures from the area of dynamic algorithms. And for enumeration, we also have a dichotomy, but only for conjunctive queries that are self-join free, so that do not occur where a relation symbol does not occur twice. So let phi be a fixed conjunctive query without self-joins. Then if it's Q hierarchical, we can enumerate the result with constant delay and constant update time. And if it's not Q hierarchical, then it's not possible to enumerate it with sublinear delay and sublinear update time, unless the online matrix vector multiplication conjecture fails. So, yeah, to get a feeling for these lower bounds, look again at the definition of Q hierarchical queries. So we have two conditions here, and there are also two typical queries that contradict these conditions. So the first one is the SET query, which is not hierarchical, because in every hierarchical query we have one vertex that is contained in every relation. And this is obviously not the case here. So we do not have such a tree for this query. And the other query is also very simple. So it's that one, it has this hierarchical form, but the quantifiers are not in the correct, at the correct place. So we have an existential quantifier here at the root, but the vertex below is not existentially quantified. So, and now I want to give some ideas why the second query, where the existential quantifier is at the wrong place, is hard for counting and enumeration. So first consider the task of enumerating with constant delay. So we reduce from the so-called online matrix vector multiplication problem, which is the following. So we have a Boolean n times n matrix M, and the stream of n Boolean vectors of dimension n. And the task is to compute the Boolean matrix vector product of M and V before the next vector arrives. And this can obviously be done in cubic time by just a trivial algorithm. And the conjecture states that we cannot do better, so that there is no truly subcubic algorithm for solving this online matrix vector multiplication problem. So why is this? So this problem is specific to dynamic algorithms, because if all vectors, if we would have received all vectors by one, so we could just do one Boolean matrix multiplication in order to get all the output vectors. And this can be done in subcubic time. So the conjecture essentially states that if we slice the matrix in columns and get them one by one, then we cannot do fast matrix multiplication. And yeah, and one thing we show is that if we have belief in the online matrix vector multiplication conjecture, then enumerating this specific query is hard. And the proof is also not very difficult. So we just let the relation E to be the relations that characterize the matrix M. So we have one edge between two numbers if and only if the entry in the matrix is 1. And then we let the relation T to be just characterizing the vector Vj after every update. So we update relation T in order that the vector V is the incident vector of the characteristic vector of the set. And we can do this because we have only n numbers. We can do this in n times our assumed update time, n to the 1 minus epsilon. And after each round, if we compute the query result on the current database, then it's not hard to see that this actually is the matrix vector multiplication of these two vectors. So we just say that there exists an index where the row of the matrix agrees with the entry of the vector. So both are 1 and the result is 1. So we could output the vector within subquadratic time, and doing this for n vectors would give us a subcubic time algorithm for the online matrix vector conjecture. Okay, so and this this idea then scales to all conjunctive queries which are not Q-hierarchical because the quantifiers are at the wrong place. And the second thing is the lower bound for counting the number of result tuples for exactly the same query. And here we have to reduce from a different conjecture, namely the orthogonal vectors conjecture. The problem here is the following. We have two sets U and V of n Boolean vectors of a specific dimension D, and the task is whether there is a vector U from U and a vector V from V such that they are orthogonal, so the product is 0. And this can obviously be done in just n squared times d. So just for all pairs of vectors, we multiply them and look if they are orthogonal. And the conjecture states that there is no truly subquadratic algorithm for that problem. If the dimension is, say, something polylogarithmic, say log squared of n. And actually, this conjecture is supported by the strong exponential time hypothesis. So if we have a faster algorithm for orthogonal vectors, we would have a faster algorithm for the K-sub problem. And now we can reduce the orthogonal vectors also to this problem. And it's also not very difficult. So in this case, we our graph has the following structure. So the right-hand side are just all vectors from the set U, all n vectors from the set U, and our left-hand side are just log squared of n vertices, which stand for the vector coordinates, and the relation E encodes all vectors from the set U. So we have an edge to the first position if the first entry is 1 in U1, and no edge to the other position if the entries are 0, and so on and so forth. And now the relation T corresponds to the vector, to one vector from the second set V. And we put vertices in that relation if and only if the corresponding coordinate is 1 from that vector. And then we see that there is a vector that is orthogonal to the current vector if and only if it has no edge in this set. So if the product is 0 between these two vectors. And this we can test by just counting the number of results of this query. So counting would be to count the number of vectors that have an edge in this set. And if it's smaller than n, we know that we have found an orthogonal pair. And if not, we proceed with the next vector. And we do it in that way and assume that we have sublinear update time. We can do it in time, say, log squared n to the 1 minus epsilon. And if we do that m times, we get an total running time of n to the 2 minus some slightly smaller epsilon prime, which would contradict the orthogonal vectors conjecture. So and this concludes the proof for these example queries, and our general proof works by essentially reducing to these specific case. So we can do this for counting by an inclusion-exclusion argument, and for enumerating it slightly, so it's more difficult, so that we have only the result for self-join-free conjunctive queries. So to conclude, so on dynamic databases, it turns out that this Q-hierarchical property characterizes the tractability of conjunctive queries in the sense that it allows constant update time, and queries that are not of this form cannot be maintained with sublinear update time. And two related works. So the first one is by Idris Ugarte and Van Zumeren. They provided a dynamic algorithm for acyclic conjunctive queries and showed that our special case of these Q-hierarchical queries, they turn out to be also efficient in practice, and they will present their paper on Thursday at SIGMOD. Furthermore, we continued working on that problem and also obtained similar characterizations of, for union of conjunctive queries. So one open problem that is also probably hard would to have a full characterization of tractable enumeration for conjunctive queries. So beyond the self-join free case, but this is also wide open even in the static setting. And this concludes my talk. Thanks.
Okay, thank you. I'm wondering, so you're exploiting here essentially at a crucial level the fact that the databases can be changed in any way. Is there, do you think that the setting changes if, for example, you have constraints on certain relations or on the way in which updates can be performed? Any insights in that respect?
Yeah, I think that that's the case. So, for example, if you have functional dependencies, it turns out that in some cases it is easier to evaluate also hard queries. So if the functional dependencies are in the correct form. On the other hand, if we consider databases that have a bounded degree, say we have only updates that respect a certain degree bound of the database, then we are actually able to enumerate, to maintain all first-order queries and also first-order queries with counting quantifiers. So then the the number of tractable queries is way larger than just this fragment of CQ.
Yeah, thanks. Just to make sure I understood properly, you said your index is a form of factorized representation. I think I heard you say F representation. So is it, it's not a D represent, like you don't need to share any common parts in this factorized representation? It doesn't help you at all to do this kind of stuff?
So no, I don't know. So we just recognized very lately that these are actually these F representations that were already considered before. So in this non-dynamic sense, yeah, probably there's something.
There's no sharing, right? It's just a tree, right? There's no sharing of subparts of the factorized representation in your context.
No, not in this sense, but might be possible.
So the difference is that when you are under updates, if you share some part, right, maybe one update will make the node on top become compatible only with that part, and therefore you cannot share, right? When you're not in the setting of updates, you can share because the things that are compatible will remain compatible, right? But when you have updates, you cannot easily share these intermediate nodes. Yeah, but then you don't have constant time updates. That's it. That's problem. Okay, can I take the moment to make a question? So the do you have any intuition on okay, maybe you don't have constant time updates, but you may have some amortized analysis over the update time. Do you have any intuition if this makes a difference, right? Instead of considering only constant time?
Yeah, so these online matrix vector conjectures also state that this problem is hard for amortized time. So this reduction would preserve that, and they will also be hard for amortized time. Yeah.
All right, let's thank all the speakers.